This is video 1 of topic 4 on evaporation and evapotranspiration. If you need more information, you can also find it in your textbook on pages 56 and 57 and from 111 through 122. The topic of this video is an introduction to evaporation. In video 2, I talk about measurements using an instrument called a Class A pan. In video 3, we talk about water and energy budget approaches as well as mass transfer approaches. In video 4, we talk about the difference between evaporation and evapotranspiration, and we look at calculation of both. And then in the synchronous session, we'll do some calculations based on those equations. Evaporation is the process by which water in its liquid or solid state is transformed into water vapor, which mixes with the atmosphere. Evapotranspiration, or ET, is considered separately as the combined loss of water vapor from the surface of plants and the evaporation of moisture from the soil. Evaporation is important in the long-term water balance. Here we mean typically weeks, months, years. It's relatively unimportant in the short term, so hours and possibly even days. It's also usually important for large-scale water resources project planning and water supply studies, especially in dry areas like Alberta. Knowledge of evaporation processes is important in predicting the water losses to evaporation, particularly from a lake or reservoir. And for a good conceptual review of the importance of evaporation, you can check this video on YouTube. I already alluded to the evaporation timescale, but to be a little bit clearer, typical storms may have an intensity of, say, 10 millimeters per hour. Okay, these are some very large storms and the runoff in the aftermath. However, evaporation is on the order of about 0.25 millimeters per hour. And so normally evaporation is neglected for flood flow studies and urban drainage applications. And you can see why. I'm not going to have less of a problem an hour later because of evaporation. It's important to consider where evaporation is situated in the hydrological cycle. It's one of the key losses or abstractions. So here's precipitation, which was the topic of the previous lecture, and here's where evaporation and evapotranspiration fit in. Evaporation is actually very important on a global scale. On average, 62% of the rainfall that occurs globally is returned to the atmosphere as evaporation or evapotranspiration. This is the single largest source of surface losses in the hydrological cycle, larger than infiltration, larger than runoff. Location is important for evaporation, so climatic factors have a significant effect. Evaporation rates are high in arid or semi-arid regions, and so in the US Southwest, as we saw with Lake Mead in the previous video, the evaporation can be very high. But it's low in humid regions. It can be, say, as low as 500 millimeters in the US Northeast and Northwest. In Alberta, the potential evapotranspiration, which we'll talk about later, is about 902 millimeters per year. The actual is lower because water isn't always available to evaporate, even if the potential is there for more evaporation. And so it's about 364 millimeters per year. Looking at global evaporation and how it varies on an annual scale, here are January evaporation rates for the entire planet. And you can see that in most of the northern hemisphere, there's very little evaporation. It's winter. And if we look at July rates, we see much higher evaporation in the northern hemisphere. And then note in the southern hemisphere, we're getting into winter, so the rates go down here. Whereas here we're in the summer in the southern hemisphere, and so evaporation levels are high. How does evaporation actually work? Well, let's imagine that we have a closed container like this that contains some water and is kept at a constant temperature. So we're not heating it, right? It's just kept sitting on a desk as it is. As evaporation proceeds, let's imagine that the air initially is kind of dry when we put the lid on the container. The pressure in the airspace above the water increases because of an increase in the partial pressure of the water vapor. Okay, so it's not at a saturation level, and so it will continue to evaporate until it reaches that level. Evaporation continues until the vapor pressure of the overlying air equals the surface water pressure, or in other words, the airspace is saturated. Further evaporation, or at least net evaporation at this point, ceases because the container is at equilibrium. That's in theory. In practice, our world doesn't look like this, right? We live in an open environment. In an open environment, then, equilibrium would not be reached, right, if that container were open to the atmosphere. In that case, all of the water we know would eventually evaporate. To get it all to evaporate, we do need thermal energy input, and that's required to allow the water molecules to escape at the air-water interface, so at the surface of the water, and the amount of heat that's required to convert all of that water to vapor at a constant temperature, we learned a couple of topics ago as the latent heat of evaporation. If you want to try a simple experiment at home, here's an experiment on YouTube. In reality, as vaporization continues over a free water surface that's open to the atmosphere, you get accumulation of vapor molecules in the air immediately above the water surface, and that causes an increase in the vapor pressure in the air just above that surface, which stops any further evaporation from occurring. So at that point, condensation begins because the air is saturated. In some cases, you can see this over a lake in the summer, where there's sort of a mist or a fog over the lake in the early morning. That's where the water, where the air is saturated right above the water surface. Again, in reality, though, even that situation of condensation immediately above the surface doesn't usually occur, and that's because we have what are called convective transport processes that prevent equilibrium from occurring. In other words, there's wind that blows across the surface of the lake and moves that saturated air aside, replenishing it with unsaturated air, and that unsaturated air then receives additional evaporation or water vapor from the water surface. Looking again at a more realistic situation then, we have a lake as an example. A lake has an open surface, it's exposed to sunlight, wind, air temperature, and so on. And so the next question is it easy to figure out evaporative losses from a lake? And the answer is, unfortunately, not. The estimation of evaporation from lakes and reservoirs is not a simple matter, as there's a number of factors that can affect the evaporation rates. Notably, the climate and physiography of the water body and its surroundings. In addition, the water has the potential to transport stored heat within the water body itself and into and out of the lake. So think of streams flowing in and streams flowing out, carrying warmer or cooler water. There's also seepage through the base, there's evaporation from the surface, there's potentially precipitation onto the surface. In other words, it's complicated. And we'll talk more about this when we get to the water budget in a couple of videos. To summarize then, evaporation from a lake is a function of solar radiation, the water temperature, the air temperature, the vapor pressure difference between water and the overlying air, and the wind speed across the lake. We'll talk next about how you can actually measure some evaporation. That's in video 2. This ends video 1.